This video is about factorizing algebraic expressions which are cyclic or symmetric or alternating, typically looking like this. Definitions of symmetric, cyclic and alternating. Symmetric expression is the expression when you replace a by b in the expression which involves abc and still the expression remains the same. It remains unchanged. So f of a comma b comma c, in any order if you put abc, the expression remains same. For example, a plus b plus c, ab plus bc plus ca, no matter you replace a by b or b by a, the expression is not going to change. So these kind of expressions are called symmetric expressions. Cyclic expressions are the ones which you have to replace the letters cyclically. That is, you replace a by b, b by c and c by a, and then you find that the expression does not change. So f of a comma b comma c is exactly equal to f of b comma c comma a is exactly equal to f of c comma a comma b. We write these cyclic sums using sigma notation. Sigma cyclic a square b means a square b plus b square c plus c square a. Every symmetric expression is automatically cyclic since cyclic shift is one of the 6 permutations. However, a cyclic expression need not be symmetric. Converse is not true. Every symmetric expression is cyclic. Next type is alternating expression. When you replace a by b, then you end up getting a negative sign and otherwise the identity is same. So f of b comma a comma c is opposite of f of a comma b comma c. In this case, we call them alternating expression. In particular, an alternating expression is 0 when any two variables are equal. So example, a square into bracket b minus c, b square into bracket c minus a plus c square into a bracket a minus b is a cyclic but alternating because you end up getting negative sign outside. E is cyclic and alternating. So key relationship is symmetric expression is always cyclic, but cyclic expression need not be symmetric. The cyclic expression can be alternating as well. The important example is as follows: the cyclic and alternating. Now let us learn the methods to solve or factorize this kind of expressions. The first method is using test for Vandermonde's factor. Now the test is if we put a is equal to b and if the given cyclic expression becomes 0, then using our factor theorem which we have done for polynomials will be true for multivariables also. So a minus b will be factor of your cyclic expression. Similarly, because the expression is cyclic, b minus c and c minus a are also going to be factors. So basically a minus b, b minus c and c minus a will divide the given expression, algebraic expression in a, b and c. Then what we will do is we will count the degree. Let the degree of p be n, the given expression, let the degree be n. Since degree of a minus b, b minus c and c minus a is 3, the degree of the factors that we have taken out together is 3, and therefore there will be another polynomial which is remaining, which is q of abc, which will have degree n minus 3. So if we can identify the type of q that we are left with, then we will get the complete factorization. Okay, if degree is 0, then you'll have to just consider a constant. If degree 1, then you'll have to consider k into a plus b plus c, and if degree 2, then you'll have to consider k1 times a square plus b square plus c square plus k2 times ab plus bc plus ca. Okay, and then finding key is the last step in this particular type of factorization. So in that what you do is you plug in the values 1, 2 or 0 simple values in the original expression, get the value of p and get the value of q, solve for k, and then you are done with the complete factorization. The method 2 involves arranging the expression in the descending powers and then factor by grouping. Choose one of the variables, treat p, a, b, c as a polynomial in one variable, say a, and arrange the terms in the descending powers of a. Group suitable terms, rearrange and group the terms so that a common bracket or a factor appears. In particular, look for factors such as a minus b, a minus c, or b minus c. Factor the common bracket. Once a common bracket is identified, factor it out and continue factorizing remaining expression in similar fashion. Repeat the process and eventually you will end up getting all the required factors a minus b, b minus c and c minus a along with the remaining expression automatically. In the first method we will have to identify the q of a comma b comma c, the expression, the last quotient we have to identify, but in the second method if you can get the three factors well, then the remaining expression is automatically available. Now let us understand both these methods by taking examples. Let us take first example of degree 3, and the example is a square inside bracket b minus c plus b square inside bracket c minus a plus c square inside bracket a minus b. By using test 1 we will solve this problem using test 1, and in test 1 we will put a is equal to b and observe that the expression becomes 0. So a minus b is a factor and it is a cyclic symmetric expression. So b minus c and c minus a are also factors. Therefore we directly get a minus b into b minus c into c minus a as factors of p. Now the degree count, if we do, the original degree of p is 3 and we have got the degree 3 of all the three factors together, and therefore the job remains is finding out the value of k. So the step 3 is we substitute some values of ABC. In this case I have substituted 0, 1 and 2 and I got the value of p equal to minus 2. Therefore I can find out the value of k is equal to p upon the value of these three brackets, which is 2, so equal to minus 1. So k comes out to be minus 1 and hence the factorization of the given expression was opposite of a minus b into b minus c into c minus a, or you can absorb that minus sign in one of the three brackets. Now let us look at the second method in example 2 by arranging the given expression in descending power and then factorizing. Okay, so the given expression is p is equal to a cube into b minus c plus b cube into c minus a plus c cube into a minus b. So let us arrange this in the descending powers of a. The first term is a cube, the coefficient is b minus c. Second term is a, whose coefficient is c cube minus b cube, and the third term is constant bc into b square minus c square. Okay, so we can look at the factorization of the coefficient of a and the constant term. C cube minus b cube gets factorized like b minus c into b square plus bc plus c square with minus sign outside, and b square minus c square gets factorized as b minus c plus b minus c into b plus c. So we obtain p as b minus c comes out, and inside the rectangular bracket you have a cube minus ab square plus bc plus c square plus bc inside bracket b plus c. Okay, so now we have to factorize further the rectangular bracket. So we arrange the rectangular bracket in the descending powers of b now. So The highest power of b is b square, its coefficient is c minus a. Then the power of b is 1 and its coefficient is c inside bracket c minus a, and the constant term is minus a into c square minus a square. So we can easily take out c minus a common. The remaining term, remaining bracket is b square plus bc minus a inside bracket c plus a. So c minus a comes out as a bracket outside the bracket as a factor, and then what remains inside is b square minus a square plus c minus b. Okay, so actually this bracket is also written in the powers of c. Okay, so the first term is constant and second term is power of c equal to 1. So you get the third factor b minus a out, and the remaining expression is a plus b plus c. Now let us look at the third example, which is a little different than what we have done earlier. The expression is degree 3 a cube plus b cube plus c cube minus 3abc, and a minus b trick does not work here directly. Instead of using that trick, because the expression is symmetric, we will now check whether a plus b plus c is a factor or what. So if a plus b plus c is equal to 0, if we try to find out whether this is a factor or not, then we substitute c is equal to opposite of a plus b and then do the calculations. If we substitute c is equal to opposite of a plus b, we get the expression to be equal to 0, and if the expression is 0, that means a plus b minus plus c is going to be a factor of the given expression. So if we do the degree count, then the first factor is of degree 1, so we'll have to find out the second factor, which is of degree 2 and is also supposed to be symmetric. So we assume the second factor to be k1 times a square plus b square plus c square and k2 times ab plus bc plus ca, and by using the old trick, by substituting values a of abc, maybe in this case 1 0 0, we get our p equal to 1 and a plus b plus c is equal to 1. So q of 1 comma 0 comma 0 is also 1, therefore k1 is equal to 1. If we substitute 1 comma 1 comma 0, then we get the value of k2 equal to minus 1, and hence we get the complete factorization of a cube plus b cube plus c cube minus 3abc, which is equal to a plus b plus c inside bracket a square plus b square plus c square minus ab minus bc minus ca. So this is the most frequently used identity in algebra, so it is better to memorize it. But the trick of factorization here is a is equal to b doesn't work. Maybe writing the expression in descending order also is not working. Therefore, we try some new factor. Because the expression is cyclic and symmetric, we can try whether a plus b plus c is also a factor or not, and that can be tried by substituting any one of the three. In our case, we have substituted c is equal to opposite of a minus b, and the expression became 0. Therefore, a plus b plus c is a factor, and then finding out the remaining factor, which is degree 2, was relatively easy. Now example 4 is application of example 3, in which we have a minus b bracket cube plus b minus c bracket cube plus c minus a bracket cube to be factorized. Now this is something similar to a cube plus b cube plus c cube minus 3abc. So if we substitute x is equal to a minus b, y is equal to b minus c, z is equal to c minus a, then we have got x plus y plus z, which is equal to 0 in LHS. So the key identity here is x plus y plus z, which is 0, and therefore x cube plus y cube plus z cube is going to be equal to 3 into x into y into z, because of the previous example which we have solved, and therefore we get the factorization directly because our left hand side xyz, which is a minus bb minus cc minus a, add up to 0. Therefore the right hand side is 3xyz, which is in the factor form. So we directly get the factorization of this given expression. So we have discussed 4 different types of problems, and majority of algebraic expressions which can be factorized, they look cyclic, symmetric or alternating, can be factorized using these methods. I hope you will find this interesting. I am giving you some more problems to solve and practice along with the answers in this video. Thank you. If you like this video, please subscribe and make sure your friends, your fellow students also get benefited by these kind of videos. So forward this information to your friends. Thank you.